Hi there. So today I'd like to talk to you about the Biot Savart Law. So first of all, Biot and Savart were physicists who conducted experiments on the force exerted by an electric current on a nearby magnet. So basically they took a compass and they put it near a wire, a current carrying wire, and they studied how it affected the compass and how it turned in the presence of the wire. And they arrived at a mathematical expression that will give the magnetic field strength and direction at some point in space due to our current. I'm going to call this point in space the point of interest as I move throughout this lecture. So first of all, here's the expression for the Biot Savart law for a moving point charge. So we're going to get to the expression for a current in a second, for a current carrying wire in a second, but let's first talk about a point charge. So the magnetic field is equal to mu naught over 4 pi times QV cross r hat over r squared. So that's the magnetic field for a moving point charge. Now the constant mu naught is the permeability of free space. The value of the permeability of free space is 4 pi times 10 to the minus 7th Teslas meters per amps. In this expression, Q is the charge. If everything is in SI units, then you need the charge in coulombs. Here V is the velocity vector. R is the distance between the charge and the point in question. That's in the bottom of the expression, r squared. So you're going to take the inverse square of the distance between the point charge and the point in question. And then r hat is the unit vector. And the unit vector points from the charge to the point in question for where you want to know the magnetic field. Now this is a vector cross product. So the direction is given by the right-hand rule. Now let's explore the direction for two different scenarios here in the next slide. So let's say first that you have a positive charge plus Q and it's moving here to the right with some velocity V. Let's say that you want to know what the magnetic field is at two different points, which I've labeled here point P1, which is above and in purple, and point P2, which is below and in blue. Now the r hat unit vector for each one of the scenarios, let's talk about P1 first, the one on top. R hat is the purple arrow here, which is pointing upward away from the positive point charge and towards this point P1. Now remember your right-hand rule. You make a gun, basically, okay? This is your first vector, this is your second vector, and this is your resultant vector. So in this case, we're going to take our index finger and point it along the direction of QV, and then our middle finger points in the r hat direction, and then our thumb gives us the resultant vector for the magnetic field at point P1. Now you can see that the way that I've got my hand oriented, P1 is pointing, or the magnetic field at P1 is pointing out of the screen. Now the way that I've shown this here is to have a dot surrounded by a circle, and that's going to be the notation that I use for a vector that's pointing out of the screen at you, okay? So that's the first one. The magnetic field at P1 is pointing out of the screen. Now let's do the magnetic field at P2. Again, my index finger is going to point in the direction of QV. My middle finger is going to point in the direction of r hat, which is down in this case, and then my thumb is the resultant vector, which is going to point into the screen at point P2. So the magnetic field at point P2 is pointing into the screen. I'm going to symbolize into the screen with an X with a circle around it, kind of like you're looking at the back side of an arrow where the feathers are making an X. Okay? All right, now let's talk about the second scenario. Yet again, we have a charge. In this case, the charge is negative charge. Now, here I've indicated the direction of the velocity with this dashed arrow, which is pointing to the right. So the negative charge is still moving to the right. But because it's the product of the charge with the velocity, QV, right? And Q here is a negative charge, then the QV vector actually points left because the negative sign flips the direction of QV, okay? So instead of pointing to the right, which is the direction of the velocity, the negative sign on our charge makes that vector point left, okay? I hope that's clear, but if it's not, pause the video and stare at it for just a second until it becomes clear, okay? So now we're going to take our right-hand rule again. in this case, since QV points left, R hat points up. Let's see if I can do this like this, okay? Then your magnetic field at point P1 points into the screen, which is symbolized here by that X with the circle around it. Now, for the QV where point P2 pointing, R hat pointing down, then my thumb points out of the screen, symbolized by the dot with the circle around it coming out of the screen at P2. So make sure you can recreate that for yourself. This is a little review of the right-hand rule. Okay, now it's worth reiterating that the SI unit of the magnetic field is called the Tesla, okay? So when you do all these multiplications of the QV cross the R hat over R squared times mu naught over 4 pi, the units that you end up with in SI units are the Tesla. Now a Tesla is a really big unit. Remember that 2 Tesla can pick up a car. MRIs that you might find in hospitals, those are about 10 Tesla. And the Earth's magnetic field is a tiny little number in comparison to all those things. 25 to 65 microtesla, for example, order of magnitude depending on where you are on the surface of the Earth. The CGS unit of the magnetic field is actually a slightly more reasonable unit, and this is the Gauss. So there's about 10 to the 4th Gauss in 1 Tesla. Okay, now we talked about it for a moving point charge, but of course, normally you don't have just one charge moving. You have a bunch of charges and it makes a current. So if you have a bunch of moving charges, then this gives you another form of the Biot Savart Law. So in this case, I'm going to express the magnetic field dB, a little differential amount of that magnetic field here. So dB is equal to mu naught over 4 pi times the current I ds cross R hat over R squared. Now here, ds is a vector, a little differential vector, that points in the direction of current flow, okay? So it points along the wire in the direction of current flow. R hat's the unit vector that points from ds to the point in question, and yet again, R is the distance from the point in question to the wire, okay? All right, so make sure that you don't confuse this expression, the Biot Savart Law, for the magnetic field that's external to the conductor, because sometimes we have scenarios where you want to know what the force is on a current carrying wire due to an external magnetic field. So make sure you don't make that mistake. Now also remember that current is always defined as the direction of positive charge flow. So the current is going to point in the direction that positive charges would flow in the circuit or in the scenario that you have. So if you have your negative charge being the current carrying object for that, then remember that that flips the direction. So your electrons, for example, that would be moving through a current carrying wire in the circuit, they move opposite to the direction that the current points. So don't forget that, okay? Since the current always points in the direction of positive charge flow, then that makes things a little bit easier, okay? There's, in addition to the right-hand rule that I just demonstrated with the positive charge carriers, there's a secondary right-hand rule that you can use. So if you do this one, then what you do is you take your right hand, you take your thumb and you point it in the direction that the current flows, and then your fingers will curl around that wire in the direction that the magnetic field will encircle the wire. Remember that magnetic fields make circles around straight current carrying segments, okay? So if you have a little ds, then your magnetic field will encircle it in that direction. So for example, in the little segment that I have here on the screen, if you have IDS pointing in the direction of the current flow, take your thumb and point that in the direction of the current flow, then the magnetic field would encircle that wire, okay? So that means that up top, it would point out at point P, right? And then it would encircle around the wire and it would be pointing into the screen at point P prime, all right? So make sure you can recreate that. Pause the video, take a second, make sure you can do it. Okay, so in order to get the total magnetic field at a point in question due to a current carrying wire, what you would have to do is you would have to integrate over the entire wire, okay? So to find the total field, you would do the following. The magnetic field would be equal to mu naught I over 4 pi times the integral of ds cross r hat over r squared. And of course that integral would be done over the entire current distribution. An example is worth 1,000 words, so let's do one. Let's do the magnetic field for a curved wire segment, okay? Here you can see the current is flowing down and to the left, and then it goes around the arc of a circle, that's subtended by some angle theta, and then it flows away, okay, straight away along the radial direction from point C to C prime. So you can see that it points inward along the radial direction of the circle as it moves from A prime to A, and then when it moves from C to C prime, it points radially outward, okay? Now the current we're going to assume is steady, so that means that I is a constant, and we're going to assume that this is the arc of a circle. So along the whole arc of that circle, the distance from the point in question, which is here called O, to ds is going to be the same distance, and that distance is the radius of that circle, which is A. Okay? Now let's get a couple of things out of the way. First of all, there's going to be no magnetic field contribution from the wire as it goes from A prime to A, and there's going to be no contribution for magnetic field at the point in question from that wire as it goes from C to C prime. And that's because here we're dealing with a vector cross product. Remember that if you take the absolute value to determine the magnitude of the vector cross product, let's say that you're doing A cross B equals C, for example, then the magnitude of that vector cross product, the magnitude of the vector C, would be the magnitude of A times the magnitude of B times the sine of the angle in between A and B. Okay? So here, what you've got is you've got r hat cross ds, or ds cross r hat, I'm sorry. So from A prime to A, ds points along the radial direction, inward towards O. And so does r hat. They both point in the same direction, inward towards the point in question, O. Because r hat is parallel to ds, then the angle in between r hat and ds is 0. And the sine of 0 is 0. So your magnetic field contribution from that straight current carrying wire segment from A prime to A will be 0 because the vector cross product magnitude gives you 0. Now the same could be said from C to C prime, right? ds in this case points radially outward, and r hat would point radially inward. That means that the angle in between ds and r hat would be 180 degrees. The sine of 180 degrees is 0, so that means that there is no magnetic field contribution for the wire segment when it moves from C to C prime. So that means that the only part of the integration that you need to perform to get the total magnetic field is from point A to point C, here along the arc of the circle. The straight segments from A prime to A and C to C prime do not contribute yet again because of the magnitude of the sine of the angle. Okay? Okay. So since we know that the straight segments don't contribute, let's figure out what the magnetic field is for the segment that does contribute, the arc of the circle between A and C. Now, what we really want is we want to know the direction and magnitude of the magnetic field at point O. So first of all, let's talk about the direction. If you point your thumb along the direction of that arcal circ, right, the arc of the circle, so here's my thumb, then my fingers would circle around like so. So at the point O, the magnetic field would be pointing into the screen as it curves around. Make sure that you can recreate that with either of the right-hand rules that you like, okay? And no matter where you are along that circle, right, along that arc, your magnetic field is still going to be pointing into the screen at point O, okay? All right, so that's the direction, into the screen. Now let's figure out what we have to do with the magnitude of that vector cross product, okay? Here we have ds cross r hat. So the magnitude of that would be ds times the magnitude of r hat times the sine of the angle in between them. Well, the magnitude of r hat is just 1 because it's a unit vector, so by definition it's 1. Now, the magnitude of ds would be a d theta, okay? Because it's a little line segment, but it's along the arc of a circle, and so ds would be a d theta. Okay, so that's the magnitude of that part. Now we just have to figure out the magnitude of the sine of the angle in between r hat and ds. Well, since r hat points radially inward always, and ds points tangent to that circle, then the radial vector and the tangent vector are always going to have a 90-degree angle in between them. And so that means that the sine of the angle is the sine of 90 degrees, which gives us 1. Okay? Okay, so remember our Biot Savart Law, mu naught I over 4 pi times the integral of ds cross r hat over r squared. Okay? So we talked about how the magnitude of that vector cross product would just give us a d theta, and then the sine of 90, of course, which is understood as 1. The r hat magnitude is 1. So the magnitude of my magnetic field here, on the top I would have for my ds cross r hat a d theta. Mu naught I over 4 pi would pull outside of the integral. Those are all constants because I is a steady current. And then we're going to divide by the distance squared between the point in question, point O, and ds. Well, that's always fixed, right? Because it's the radius of a circle. So here we have divided by a squared, which is the radius of our circle. Now, we have a over a squared that pulls out. A is a constant, so that pulls out as 1 over a. So outside of the integral, we would then have mu naught I over 4 pi a, and then times the integral of d theta. Well, if you integrate d theta, you just get theta. So that means that our magnetic field magnitude at point O would be mu naught I theta over 4 pi a. And that would be the magnetic field at the center of an arc of a circle. Okay? Pause that if you need a second to figure it out and stare at it. Now, if you think about you having a full loop so that the magnetic field makes a complete circle, or the current makes a complete circle, and we want the magnetic field at the center of that loop, then theta would go to 2 pi, which is the angle subtended in a complete circle. So then you would plug in for that, mu naught I over 4 pi a times theta. Theta would be 2 pi, and that would leave you with mu naught I over 2a. And that would be the magnetic field at the center of a full loop of current. Okay? Now, if you're talking about what the magnetic field would be like off axis, then let's say that you're interested in the magnetic field at a point in question that's along the center of the loop but some distance x away. Now I'm going to give you this derivation in the notes, which I'll post below the lecture, but for now the magnitude of that magnetic field is mu naught I a squared over 2 times a squared plus x squared to the 3/2 power. Okay? Now this is done in your book. It's done on page 299 of Purcell and Morin's Electricity and Magnetism 3rd edition in section 6.5, so you can look that up. And you can also, if you prefer, look at my notes will be posted underneath this lecture on our course website. Okay? So there's that. Now, you can see here that the magnetic field strength is going to decrease the further away you get from the center of that loop. So what would this look like? Okay, well, if you have a current carrying loop, the magnetic field is going to make little circles around the wire as it goes through the whole loop. And so it acts like a little bar magnet. If you take your fingers, curl them in the direction of the current, your thumb would point in the direction of the magnetic field at the center of that loop. And that would act like the north pole of the magnet. It would point away from there, and then it would encircle around and loop around the loop in all directions and come back around to the south pole of our little magnet. Okay? So that's what the magnetic field lines look like for a current carrying loop. It represents very similar to a tiny bar magnet. Okay, I hope you could follow that and find it interesting, and I'll see you around. Make sure to send me a note if you didn't understand anything, and we'll catch up on Zoom.